As you dive into calculus and differentiation, you're going to require more rules that will help you differentiate complex functions. So you've already seen the chain rule previously, and you're going to now use it simultaneously or just separately with product rule and quotient rule. So we have different purposes for all of these rules. The chain rule is mainly used when you have a function inside another function, and the product rule is used when you have two functions multiplying with each other. So I'm going to explain what this means, but it's best understood through an example. So if I have the product rule, it states that if you have a function that looks like it's being multiplied by two other functions, so it's equal to two other functions multiplying, then the derivative of your f of x is going to be taking the first kind of sub function, if you want to call it, the first one, multiply the derivative of the second, plus the second one just originally multiplied by the derivative of the first one. So kind of like playing tag here. So if I have my function, this is my function, and I can recognize that it's a product of two things. So I can write it as a u times v. So this could be my u and this could be my v. Remember, you want them multiplying with each other, and it's going to be obvious the more examples you're going to see. So we're going to identify our u and our v. So here they are. I'm going to take them out, and then what I'm going to do is I'm going to differentiate both of them. You can easily use the power rule for these ones, so no need for complex processes. So u prime and v prime are given here. Now, if I want to differentiate, what I'm going to do is I'm going to take the original u multiplied by the derivative of v plus the derivative of u multiplied by the original v, or like switch them around, whatever way you want to see it. So I have my f prime of x, so this is my original u, and this is my original v, and they're both multiplied by the derivative of the other function. Okay, so highlighted here. So hopefully you can see the matching. Do pause the video, try to see what's happening here as well so that you're on track. And then that's it, that's the derivative, but obviously we want to simplify it, so we're going to expand out here, and you're going to also expand out here. Be careful, this is like a two bracket expansion, and what you're going to get is something this long, and we're going to basically just take the like terms. So I'm going to combine these and these. So it's just basic algebra here, and that's going to simplify to this. So we actually got to the derivative here, but obviously you need to expand and simplify to make sure that you get to the final solution. So let's do a bit of a complex example. So if I have x squared, square root x squared plus 1, same thing, I want to write it as two functions. Sorry, this should say y. So I want to write y in terms of two functions, and this could be my first function, and the square root x squared plus 1 could be my other function. So I'm gonna write them as such. Now the v, hopefully you know by now that you don't deal with square roots. You'd convert the square root to a power of a half. Now this, if I'm going to start differentiating now, just I did with the previous slide, the v, if you notice, is where you might need to use the chain rule, where this is u and this is, you can substitute u in there, another letter, not u, let's say a. So you'll have to use the chain rule for this one. So I'm going to assume you've seen the video on chain rule and you know how to do it. So we have u prime is 2x and v prime after using the chain rule, so it's a bit of a longer process on the side, you're going to end up with this expression. So back to our dy by dx is going to be the original u multiplied by the derivative v, and then the original v multiplied by the derivative u. So you can see this is my original u and this is my original v, and then they're multiplied by the derivative of the other function. And then that's it. I can expand this out, so it's going to give me x cubed, and then the denominator stays the same, and then this doesn't simplify further, so we have 2x and then root x squared plus 1. So that's the final answer. I'm going to show how you can use the chain rule for this one, just so that in case you weren't clear, I can use it on the side. If you understood so far, you could stop the video here. So for using the chain rule on the side. So what I'm going to do is I have my v equals to x squared plus 1 to the power of a half. What I'm going to do is I'm going to do a substitution. So let's say I call we can't use the letter u, or we're going to call it m is equal to x squared plus 1. Okay, which means that v can be written as m to the power of a half. So what you actually want, so this v prime is actually dv over dx. Yeah, so this is the goal. Be comfortable with changing notation. Usually it's dy over dx, but in this case it's dv over dx. That's what you want. Pretend this is like a separate question. So in order to get dv over dx, I need to first do dv over dm multiplied by dm over dx. Now, the derivative of m to the power of a half is going to be 1 over 2m to the power of a half. And the derivative of m is going to be just 2x. Okay, so this is dv, because the v prime here, it's going to be a half m to the power negative a half, which is basically 1 over m to the power of a half. Just the negative becomes a reciprocal. So now if I want to simplify this final expression, the 2 and the 2 will cancel out, so I'm left with 1 x over m to the power of a half, and then we kind of undo the substitution. So I have x over x squared plus 1 to the power of a half. It just means that it's the square root. So we go back to this one. So again, remember, your goal was dv over dx. In order to find it, you find the derivative of this new expression multiplied by the derivative of your substituted expression. Go back to the chain rule video to get more details on how it's done. The only difference here is that we're using different letters.